All right. Let's look at this slightly different sorting problem. Sort integer arrays without range limitation. Look at this, without. In the counting sort, we have strict, strong range limitation. Now we want to remove that limit, that range limitation. Can we still sort an integer array efficiently? Yeah, so that's the new problem we need to solve. All right. So given an integer array, here we remove that range condition. How to sort it efficiently? We still want to sort it efficiently. What do you mean efficiently here? Definitely it must be better than big theta of n log n, right? N log n. Because we have many existing sorting algorithms that can do this better. If you only get this much, then we do not need to find a new sorting algorithm. So we should do better than this. All right? But how better we should expect? Definitely we cannot expect to get as better as linear. So the one should be somewhere between these two. Worse than big theta of n and better than big theta of n log n. That's our expectation. All right. So let's take a look at this in more details. So not linear, but near linear. Okay? Slightly worse than this linear, this growth function, but better than this growth function. Slightly worse. Yeah. All right. Next, because in order to do this, we need to pay some cost. So we have to pay some cost. Okay? Right. So we need to pay the cost to overcome the range limitation. Okay? Yeah. So that's why we need slightly worse than linear. Okay? Yeah. So you by removing the range limitation, it's not free. Okay? So we need to pay that, let's say n to the epsilon. Okay? This epsilon, very small positive integer. Okay? Yeah, actually not that. Yeah, because look at this. Log n can beat an epsilon, right? Log n can beat that. So it is very hard to describe. Log something, all right? So let's say log something. Log something. Okay? Yeah. But that function should be smaller than log of n. Okay? All right. How to solve it? All right. Our strategy, general problem solving strategy in this situation, usually we connect the current problem to something that is pretty close to our current problem. We just did one very close to it, but not exactly the same. See, we want to make that as our starting point. So that is obviously the counting sort. We just learned it. Yeah. But the gap, there is a gap. So we need to bridge the gap. We need to do something special to bridge the gap. All right. How to take advantage of integer properties. Yeah. All right. So let's, look at more properties. So here, what do we have? We don't have any range constraint on our integer values. So we cannot apply the counting sort directly. Okay? Yeah. Don't apply your counting sort directly. So it will be very bad. The performance will be very bad. Don't try to do it. All right. So now the question. How to convert no range constraint. So right now we have no range constraint to with range constraint. Can we bridge the gap in this way? That's the gap we bridge with range constraint. If we can do that, then we can apply the counting sort directly. Yeah. So let's try. Yeah. All right. By some properties of integers. Yeah. Digit-wise view. We need to use a special view here. Digit-wise view, adding range condition. Yeah. So that's an interesting view we can take. All right. So now our view is processing an integer digit by digit. Digit by digit. Can we do that? Okay. So an integer is composed of digits, right? Yeah. So can we apply counting sort digit by digit? Not on the whole integer. So that's the new view. Now let's look at if this idea helps or not. We need to investigate. All right. So why we take this view? Original data, there is no range. How do we add range condition to it? Yeah. So we change the view. Our view, new view, treat the integer as a set of digits. Okay? Yeah. Each digit has a range. That's what I need. The digit has a range, right? So that's the thing we really need. Decimal, the range from 0 to 9. That's the desired property we need. Okay? Yeah. So we finally get it. We get this natural range. Is this range natural? Very natural. So we get a natural range. All right. So here, so the idea like this. Sort the array multiple times. Because digit by digit, each digit you need to sort one time. So multiple times based on individual digits. So the idea is so simple. Yeah. But the problem is this way better than n log n? Yeah. Theoretically better than n log n? Yeah. So let's, look in more details. Data range analysis. We need to know if this idea really can give us good performance. All right. So now we have data with data size n. And we can use R digits. So because each integer has certain number of digits. Let's say the maximum number of digits for our individual integers is this R number. Okay? Yeah. So now let's try to estimate this R number. Okay? Yeah. All right. So what's the relationship between the range and R? There should be some relationship. So we want to use the integer property to do the estimation. All right. So we have this general expression, n equals decimal expression. We have that. Okay. So specifically, we can write in this way. Then let's estimate the range, the maximum number that can be represented using R digits. Yeah. So let's write it this way. So this n number using R digits, what is the largest possible number? Yeah. This is the largest possible number. Okay? Yeah. Then we can simplify again this one. Can you see that? Can you see why this number equals that? All right. So here, I hope you know that there is an algebra formula. Okay. Yeah. Algebra formula. Yeah. Let me write. A to the rth power minus b to the rth power. A minus b, ar minus 1 plus ar minus 2b plus dot dot dot. A br minus 2 plus br minus 1. That is the formula. If you know this formula, here we can use that. A equals 10. B equals 1. Look at this. A to the rth minus b to the rth. Okay? A minus 1, that's 9, right? So then, the remaining, right? Yeah. Right. So 10 to the r minus 1 plus 10 to the r minus 2 times 1, right? Plus 10 plus 1. Okay? Yeah. You need to be familiar with that formula because we need to use that formula many, many times. Yeah. All right. With that, then we can get this inequality. After simplification, we get this inequality. Then we take log base 10. This r is greater or equal to this log expression. Okay? So we get an estimate. Yeah. So we get this estimate. Yeah. This n related to the range. Right? Range. Okay? Yeah. So next, we can connect the range and the R. Okay, yeah. So assume the upper bound of the range is capital R. So big, yeah. And non-negative integer data, yeah, to make our discussion simpler. Yeah. So if we have negative data, so we can do some conversion. Right? Yeah. So we are okay, so we can consider a simpler case first. Yeah. Then the number of digits used to represent the data from our previous slide, the formula is like this. So this is the digit number estimation. Okay, yeah. So here you can see we have this log. But this log is applied on the range capital R. Range capital R. It is not applied on the data size n. Okay? So that's different. Okay? The size, the capital R. and the data size quite different. Okay, yeah. So the conclusion, the larger the range, the more digits are needed. Yeah. Okay, yeah. So if the range is too large, so probably the method is not as good as n log n, right? Yeah, because that R could be too large, right? If this capital R is too large, then this method may not be better than our other sorting algorithms. Yeah. So, but sometimes, we can say sometimes it is better than these algorithms. Yeah. All right. Yeah, but the thing is, there may not be a direct relationship between the range and the data size. Yeah. So, because in certain range, we can put large number of data items in that range. So there is no direct, strict relationship. We allow duplicate elements, right? Yeah. So that's why, it is very hard to really get a clear idea, this method always better than that one. Yeah. So in our intuition, if the range is not too bad, so this method should be better. But if the range is too large, then that method could be better. Yeah. All right. Yeah, so the data size is n. Okay, yeah. So that's the part one. Yeah. Next, so we try to, do the sorting.